So hey guys, and welcome back to this video, which is I'm sorry I forgot 3 years ago to make this video, but here's what we're doing. 3 years ago, I made a video about Coulomb's law, and I've recently been called out that I was supposed to make a follow-up electric field video, which somehow or another I did forget. So before we start talking about an electric field, because this is one of those things, maybe you felt your arm hair stand up next to an old television set, and by old I mean the kind that haven't been made in 15 years. You're not too familiar with an electric field. So let's do this. Let's look at a field that you probably are familiar with. So I'm going to draw an object over here. I'm going to, let's see how good my artwork is here. Oh, yeah, yeah, yeah. This is, that's, hey, that's not too bad. Do, do, do. Hopefully you can kind of, okay, it's starting to kind of poop out here, right? Hopefully you get the idea that what we're looking at here, let's call this big M. So here is our Earth. A field that you are familiar with is a gravitational field. So if we think about this, gravity is a field around our planet. Now, here's the thing that I think has ruined a lot of you. You're in your class and you've written 9.8, and every time you wrote about gravity, you wrote 9.8 meters per second square. I guess the shame about that is that's an acceleration due to an object moving under the influence of gravity. Gravity itself is actually a field with a strength of 9.8 newtons per kilogram. And that's the way we should really be looking at gravity as a field. And so it is a field going around the Earth, as it were. And that field is always directed directly towards the Earth. And so what happens is if we take a object, let's say we take an object here of mass M, and place in that field, the effect is this. There is a force of gravity on that object in the field, and we calculate it by taking the mass of the object, multiplying it times gravity. And again, we're always sitting here thinking about 9.8 meters per second square. Well, stop that. Start thinking about gravity as a field. And so the thing is this, one of the things we know, if gravity is a field, it changes as you get farther away from the Earth. That gravitational field strength changes. We have an equation for that in physics. Little g is equal to big G times the mass of the object divided by the radius square. And we get this equation from universal gravitation. And so I want you to think about something. So what this means is this. If you give me a radius, any radius, I can plug into this equation. I can tell you a field strength that I can then take, plug that field strength back in here, and I can tell you the force of gravity on an object at any location. Here's the thing. What we're doing in electric fields, it's the same. If you understand the concept behind gravitational fields, guys, you're already a killer at electric fields. Because what happens with an electric field, it's the same thing. Positive particles, positive particles have a field, and that field we're going to denote by letter E, this electric field, and it's going straight at them. So we've got this electric field that's going straight at this positive particle. Now the cool thing is if we had a negative particle, then the fields run away from the negative particles. And that's what's important for you to be able to recognize. Matter of fact, if we wanted to really get cool with all this, basically it's kind of like a magnet. If you have a positive and a negative next to each other, what you would see is this phenomena taking place. You would see the two fields running from one to the other in a matter such as this. And just like with magnets or anything else, the closer, the more concentrated these lines are, the stronger the magnetic field, or the stronger the electric field, the more spread out they are, the weaker the strength of the field is. Well, here's the thing. Just like in terms of Earth's gravitational field over here, we've got an equation in physics that we can use to determine that field strength. E is equal to, in this case, K Q over R square. I want you to look. Do you notice anything familiar about this? And so, just like gravitational, this is what's cool. We solved this out. Gravitational field strength is newtons per kilogram. But in the case of electric fields, it's newtons per coulomb because coulomb is this basic charge. And I'm going to do something. I'm going to make this right. Let me change my font just a little here. Can I get just a little smaller? Boom. So if you notice something, I put absolute values around the charge, and I did that for a reason, obviously. I'm not interested in terms of the positive or negative of the charge. I do have a use for positive or negative, but that's just like in Coulomb's law. The positive and negative is solely for the point of telling me, does the field lines move away or towards an object? So here's what's cool. You give me a radius from any charge and you give me that charge, I can then plug in and I can tell you the electric field. Let's just go back to the one that we were looking at a second ago. I can go back to this point and now I can tell you the actual electric field at this point R away from there. And now, just like in terms of gravity, I can then also tell you the force. So the force of the electric field is equal to Q times the electric field strength. Just like, and once again, I'm going to do something here. Boom. Let's do this because I'm doing the absolute values again at this point. So you've got a basic understanding of all this. So you see the similarity that exists. I've got charge and gravitational fields. I've got a formula for gravitational fields. I've also got one for electric fields. And then if I know that electric field, and now this is important. I want you to go back to this equation for a second because I do need to do a little something here to clean up. I'm going to put a little Q0 or Q naught there because what happens is the Q in this charge Q, this is not talking about the source of the electric field. This Q is actually talking about what we might call a test particle. So this is an object that's placed into the field of another object. Kind of like in terms of you right now being on the earth. You are the test particle around the big M, which is the earth. And so I want to kind of specify that. So this would be like the Q0 up here, while this is the Q. That was a lot. So let's go in and actually let's just do the problem from like 3 years ago at this point. So here's what the problem was. Sometimes they're nice. They give you two objects, three. Guys, they could give you five objects. It really doesn't matter. But eventually, what it will have you do at some point, you'll go to a point in space like this, and it will say, find the electric field at this point. Well, the thing is, there's three electric fields at this point. So if you look, I've got a 2 nanocoulomb charge here. So I've got an electric field due to the 2 charge there. So I'm going to call that one E2 just for my own note taking. And then I've got a 2 nanocoulomb charge down here. Well, again, fields run towards positive charges. So I've also got an electric field. I'm just going to call it E2 as well. I don't mind that notation because this was a square. So it means the magnitudes of both these vectors are the same. They're just a different direction. And then this is a -3 charge. And so what's neat about the -3 charge is this one, field lines run away from negative particles. And we'll just call this E. And you may be wondering, well, why don't you call it E -3? Well, I really don't have to. I could call it EA, B, and EC for that matter. So we've got a pretty good foundation here. So let's go back and do something else. I know that this is a square, so I know that's a 45-degree angle. And so, guys, the only thing I've left to do at this point, I need to actually, drawing the Greek letter, I need to actually find what E2 is. Well, the formula for E is essentially electric fields is KQ over R square, and that's the way most textbooks write them out. So K is a constant. Hopefully you remember K constant 8.99 times 10 to the 9. It's an easy one to remember, or 9 times 10 to the 9. I apologize for not writing out the units for this video, but I'm also not even going to write it out. I'm just going to write K times, and then here's the thing. So that's a 2 nanocoulomb charge, so it's very important for me to keep in my head that nano is -9, or I'm going to completely mess up this problem. And then I'm going to divide that by 2 millimeters because that was my radius, right? This thing has every side is 2 millimeters. I am going to go ahead and write 2 times 10 to the -3 though, just so I don't forget. And then what most people forget are the squares on there. And so there we got it. So let's do something. Let's bring out a Casio. So 8.99 exponent 9 times 2 exponent -9 divided by 2 exponent -3 square equals, and there I've got my electric field, which in this case is insanely massive. Matter of fact, it has me wanting to revisit this thing for a second to see exactly what in the world. And so pausing, and here's the funny thing is, yep, I'm perfectly good with my math, but I didn't want to double check it before I wrote down that number. So my electric field, so E2 is equal to, threw me off guard. That's why I double checked my math off camera there for a second. Let's see, I'm gonna write 4.5. I'm gonna do this, mega newtons per coulomb because I'm too lazy to write out that huge thing. So a meganewton per coulomb. And now for E3, for charge E3, we know the equation KQ over R square. So that's going to be K times, it's a 3 nanocoulomb, but remember something. This is really a absolute value, so I'm not interested in the negative. I've already used the negative for all I'm going to use it for, and that was just to tell me the direction to draw the electric fields at that point. So let's see if we can throw this in here. So that would be 3 nanocoulombs divided by, and I'm gonna have to do a little math here for a second because here's what's funny. This is a square, which means this would actually be this distance. So this distance across the middle, that would be 2 square plus 2 square, which would be 2 square roots of 2. Doing in my head, unfortunately, in math, I need an actual number for 2 square roots of 2. So let's see what if we can do 2 square roots. What is that? 2.8? I'm not even going to do it. I feel very good about that in my head. 2.8, watch me mess up the entire video now. 2.8 times 10 to the -3. If I mess that up, then, just forgive me. Let's go in and take the calculator now and actually grab this thing. Okay, I can't help myself. Square root of 8, 2.8. Sorry, I was willing to go with it for a second. I was like, I got too scared. That's called I lost my nerve. Exponent 9 times 3 exponent -9. Again, students miss these problems because they forget their exponents. Divide by 2.8 exponent -3, and then they usually forget to do this square at this part. And let's see what we get for a number on this one. 3.44 meganewtons. So this one is here, and I'll make it easy. 3.4 meganewtons per coulomb is my field at that point due to E3. So guys, we've got our values for the electric field. So the thing is, if you get this, the rest of this problem is just a vector addition problem. That's all that it is now. Let's see if we can't try and work through and finish this out. If you're very good with your vector addition, you're good. You're excused. Go home. Enjoy the rest of your afternoon. So hopefully again you understand why I had to do the Pythagorean here and find the distance between these 2 points in space. So now I'm going to do something. I'm going to add up all of my electric fields in the x direction. I'm going to add up all of my electric fields in the y direction. I'm also going to hope that my goofy computer will work. There it goes. So I'm going to go back here and look. So electric fields in the x direction, I've got this E3, which is 3.4, and I'm just going to remember this meganewtons in here. So I'm going to have a 3.4, let's see, that would be cosine of 45 minus my other charge. So I'll look for a negative x, so that's E2, so minus 4.5, and that would be equal to something. And then I'm going to do the same thing for my y. So I've got a component of E3, so that would be 3.4 sine of 45. And then I'm going to subtract the negative. So that's my E2, so that's 4.5. Guys, I got to be honest, if you're to this part in physics and you're watching this and you're getting lost, you really need to go back to an older video to play a catch up. So 3.4 cosine, making sure my calculator is in the right mode, minus 4.5. So this negative, so this would be, I come up with negative, I'm going to say negative 2.1, and that would be a mega Newton per Coulomb electric field. And now let's go back and take a look at the other one, 3.4 sine of 45 minus 4.5. What we get on that, and we got the exact, so we've got in terms of the y, we've got a negative 2.1, and my unit was a meganewton per coulomb on that as well. Here's what's neat, that makes doing the rest of this math very easy, right? So what does my final electric field look like at that point? It means my electric field is essentially, I've got an electric field in the X that's left of 2.1. I've got electric field that's down 2.1. And so if I want to know what my resultant electric field is, I messed that up, didn't I? If I want to know my resultant electric field, it's just like finding a resultant force. I have no way of writing. Let's just say I'm going to call this my ER. I'm going to call this my resultant electric field here. All I have to do is 2.1 square plus 2.1 square. And again, if you're watching this and you're going, and you're watching saying, Jason, you didn't use your negatives. Yes, I did. They just told me my directions up here. That was it. 2.1 square plus 2.1 square. Thank you, Mr. Pythagoras. Give me a square root. Answer equals 2.9. So we'll just say 3. So my resultant field is a 3.0 mega neutron per Coulomb charge. So that is my resultant electric field. And here's the thing, if I needed to do the angle, I could do theta equals tangent -1. My opposite, which my opposite would be my y. So that would be my opposite. This would be my adjacent. So it'd be 2.1 over 2.1, which means I'd be taking the inverse tangent of 1, which is 45 degrees. And so here is my final bit of information. The problem could also then come back and put a charge at this point and say, okay, well, what does it look like at this point for charge? Well, if it does that, well, that's not too bad. I know that force for an electric field is equal to the charge times the electric field. So let's say somebody places a -3 nanocoulomb charge at that spot that we were just referencing. Okay, well, if somebody wants to do that, that's perfectly fine. You can do that. So we would just drop the negative. So we'd say 3 nanocoulombs times my electric field is 3 meganeutrons per meganeutrons. Have I been saying that the whole video? If so, excuse my dumbness today. Meganewtons per coulomb meganeutrons. It's a meganeutron, quick. Look out. Now, this is pretty interesting here. We don't really need a calculator for this. 3 times 3 is 9. And if we look, that's times 10 to the negative 9. Mega is times 10 to the 6. Whoa, we are totally killing it. 3 exponent negative 9 times 3. Uh, okay, so my brain's barely functioning. 3 to the 6. And look at what we got. 9 times 10 to the negative 3. And that would be newtons of force, or we could even say 9 millinewtons. Ladies and gentlemen, we have just kicked a goal with electric fields. I hope you've watched this and this helps you in some way. Thanks for watching, guys. Bye.